a report kind of thing.
Oh, so like a report kind of thing?
Yeah, so they have to change it. You can't give the test for every single sack. Maybe do a few pracs and then do a report on the pracs that you've done. Kind of, they have to vary things.
Like they showed us like we were doing, let me see if I have it. We were doing a prac yesterday on putting a magnet through a solenoid, and we had to draw it. We had to draw the so we put a galvanometer and then we had to draw it up.
Okay. We'll see whether we can finish it off as much as possible. I think some other people having a SAC everything Unit 3 this week as well. We went through DC generator and AC generator, right?
Yep, correct, last week.
Okay, last week. We'll talk about transformers and transmission. How is Nicholas going?
Hey.
Yeah. So I don't know, most likely I will be able to start face to face, but I haven't get a clearance from Adira yet, but I'll talk to him again this week and then see whether I can start the classes next week face to face. Now, Kishan, Akshat, who else here? You guys having your SAC this week, right?
Yep.
Did you get that summary question, like the revision question I sent?
Yeah, we did.
Yeah. So that's including motion and electric power. Just go through the questions because that's the area that they're picking up questions from earlier. I don't know. So this year. So that's where some, like I see that last 2, 3 years, they're picking up questions from these old trial exams.
Yeah, okay, cool.
Have a look.
Thanks.
Okay. We can give it a start. Now, just a quick recap. Hassan, how did you go with your SAC? Was okay?
Yeah, it was good, sir.
Okay, excellent. Okay, Jaden, what about you? Do you have any SACs coming up, or you finish all the SACs?
I have one on Thursday.
This coming Thursday?
Yeah.
Is it on what? Is it on fields or is it on?
Power, I think.
Power generation, okay. Yeah. So just to recap, we went through AC generator. And went through DC generator. In AC generator, you have slip rings. So that's pretty much AC generator and some sort of a cranking mechanism. And the brushes produce the electrical contact and you supply that power to the external circuit. This could be a globe. You can see the direction of the induced current is changing every half rotation. Initially, it's going from B to A this way. That's why we saw the magnetic flux variation was like a cos graph, and EMF like a sine graph. That's really the maximum. Now, in a question, if they ask you, situation like this, because we can start the coil from anywhere you want, right? So if they say the flux is starting somewhere in the middle and the flux varying like this, ask you to plot the EMF time graph. How do you plot it? So plot the EMF time graph. People are very quick in getting the derivative. You can get the answer. What's the shape of the graph should be you expecting? If they give the flux variation is like that, ask you to plot EMF time graph. While you guys are plotting, I'll just put some numbers to calculate the average EMF as well. Calculate the average EMF. Hey, people, Praveen, whoever joined in now from Melbourne, hi people, just at least go through some of the questions, that summary questions I send you, the revision question in 3. Okay, just have a look those questions, go through it. I'm just guessing, but I'll just encourage you to go through it. Okay, plot EMF time graph. What do you get? Yep, I get some answers coming up. Justin, a cost graph. Yeah. Because you always look for the negative derivative. Because remember the EMF, average EMF, if you look at even average EMF graph, because you have the negative sign and the N is there, and you're looking for the derivative flux time graph. So always look for negative derivative. Negative derivative. So you can see that the maximum, the minimum gradient, the greatest minimum gradient, that means you're starting from the maximum. You're starting from max. It goes like that. So these are 0. It's like a normal cost graph. At this point, you get that. Does that make sense, everyone? If you can't get your head around, sir, is the EMF for a 90-degree turn? Yeah. So that's average is 90-degree turn. So this question is just for when you're looking for the average EMF, we're looking for 90-degree rotation. Average EMF looking for 90-degree rotation. Now, if you can't figure out, like generally you guys all do maths, so you can easily work out negative derivative. But in case if you're having trouble, especially under exam conditions, like if you, there's a simple way, cheap way of doing it. What you can do, you can put your flux time graph and the EMF time graph in your cheat sheet. This is the flux time graph. Draw a few cycles, maybe. Keep like that, that's your flux time graph. Then you can draw your EMF time graph on the side. It's like a sine graph. This is like a standard one, typical one. That's the EMF time graph. So I was asking you to plot from here because your flux was starting here, this position. You can get a piece of paper and cover it, and then you can plot the rest. So that's where you're starting. So you can plot like that. So that's what expecting your cost graph. So for the EMF. But if you are pretty good at quickly getting negative derivative, that's fine as well. But otherwise, I generally recommend you just put that one in your cheat sheet. So you can just cover one, so you don't need to think too much. Or you can double check. You do get the negative derivative and quickly double check whether your answer is right. That's one way of doing it. Okay, calculate the average EMF, guys, from the numbers I gave. So the B is 1.5 Tesla, AB is 20, BC is 15. Number of turns 20, frequency is 20. But number of turns 200. Tisara, Tisara. So just go through that revision questions I send you.
Yeah, will do.
Yeah, because in the past, they tend to get questions from that region of trial exams. Okay. I'll go to the DC generator. For just quickly work it out. Whenever we calculate the average EMF, we're looking for the 90-degree rotation. That's where the maximum flux change happening. Consider the flux change from maximum to minimum. Just that generally 90 degrees. It could be minimum to maximum. It's a 90-degree rotation. You can take 180 and get, so if you take that, your delta T is equal to quarter of a period because that's only 90-degree rotation. The delta T is a quarter of a period. It's a very common mistake. People are using full period when you calculate the average EMF. So we're looking at the maximum flux change, maximum to 0. So take that T on 4. So you go back to this average EMF equation and sort out the values that you need, and then plug the values back into the equation. Final minus initial. That's the final flux because when you rotate 90 degrees, it becomes 0. Initial flux was 1.5 times B times A, 0.2 times 0.15 Weber. And your frequency, maybe I'll write here, frequency was 20 Hertz. Your period was 1 on 20, which is 5 over 100, 0.05 seconds. Therefore, your delta T going to be 0.05 divided by 4. So the average EMF, number of turns, you get a negative answer. Even your final answer is negative, we give is the magnitude. 1.5 divided by 0.05 divide by 4, you can bring the 4 to the top. Anyone got number? Yes, Praveen, you got it. 720, yeah. 720 volts. Okay, that's how you calculate the average EMF. Okay. That's how you calculate the average EMF. So wherever you connect, now everyone, I just asked a couple of kids from the previous classes, 3-4 classes, everyone familiar with the cathode ray oscilloscope? Have you seen a cathode ray oscilloscope? A crow? Sometimes they call, the people are calling it a scope, oscilloscope, crow, CRO, all the terms are using for this. Who haven't seen it? Cathode ray oscilloscope. Sometimes they can give you in a question, sometimes they mention in a question. Something like this. I'll just quickly get in. I just didn't get any professional version one, but I'll quickly share the screen. I'm pretty sure you guys seen it because every school should have one, or not one, more than one, I guess. Now, this thing, have you guys seen it? Cathode ray oscilloscope, yeah, you've seen it. So you have 2 channels you can input. This is the device. You can see the whole profile. If it is a sine graph, that's the profile, you can see the sine graph. But if you connect your voltmeter or ammeter, what you get is like a single number. That number could be a RMS or average value, not the profile. If you want to see the profile, you need to connect a cathode ray oscilloscope. At least you guys need to familiar with it, what the scales are. The vertical scale, either it's magnitude, it treats the voltage, but it'll give you some sort of scale on the side. X-axis always the time. X-axis always the time. Maybe I'll make up some questions later on. I'll just stop sharing. Okay, so just get familiar with the cathode ray oscilloscope. If I connect the cathode ray oscilloscope here, that's my screen. I should be able to see a sine graph. If I connect the cathode ray oscilloscope here somehow without tangling the wires, just say I connect it somehow, I still should be able to get like a sine graph. Okay. Now go back to this is okay. Yeah, everyone okay? How to calculate the average EMF? I don't want to emphasize that anymore. Yes. And always remember the factors that influence the EMF is N, A, B, F. These are the factors influencing your EMF. Now, go back to our DC generator. Because remember, we replace the slip rings with split ring commutator. Okay. What we had was that so starting from that position, something like that. That's your globe. You could remember when you're rotating it, the induced current direction is same Here, there is no change. It reverses the direction every half rotation, but it's all the change happening here. The current direction only flowing in one direction. Now, my question, if I connect a cathode ray oscilloscope here, what would be the trace looks like? And then if I connect a cathode ray oscilloscope here, what the trace should be looks like. These are two different locations, here and here. What would be the trace? What would be the trace? I say location 1, location 2. Yeah, where is that? Your answer is relating to the top. Ah, yeah, you give me both answers, I guess. Yes, yes, that's correct. Yes. Yeah. Yeah, it's clear. It's clear. So, what kind of shape you would see here? What are you expecting here? This is a DC generator. What kind of a graph you expect here? People having a sack this week, please answer. What do you get there and what do you get there? Here, number one place, here, it will be normal sine graph. It will be that because we're not doing any changes there. EMF will be exactly like that. Okay, here, that's all happening here. That's where you get that modulus graph. So that's where you get that pulse DC graph. It's here, number 2. Be clear with that. Okay, yeah, sine and mod graph, yes. That's correct, Akshat. So the mod graph is here. Sine graph there. If they ask you to plot the flux time graph, there is no difference between the DC generator and AC generator. The flux time graph would be exactly the same. No difference. Yeah, you can, because it depends on how you connect your the cathode ray oscilloscope. If they connect your terminals other way around, you can have completely fit graph. You can have that. If you swap your terminals, connecting terminals there, maybe get the other wire and connect here, and if you swap it, you get that. Yeah, Kishan, yes, you can, as long as the current flow is only one direction. Okay, so both possible. All right, so just want to move on. So you guys have a hopefully fair understanding about the generator, and also be clear the function of the split ring commutator. Do not mix up with the split ring commutator of a DC motor. Okay, here what it does is it's reverse the direction of the output current every half a rotation. Therefore, the induced AC current in the coil become DC through the external circuit. That's the function of here. But for a split ring commutator in a DC motor, it reverses the direction of the current in the coil because we supply the power from here, and which enable the coil to rotate in one direction continuously. Do not mix up the two answers. It's a very quick common problem. When they ask you to explain the function of the split ring commutator for a DC generator, they can start writing the function for a DC motor. You have to be very clear the difference. Okay. All right, so we'll move on. I'll quickly go through the RMS peak to peak values for AC power supply. And then go through the transformers and power transmission. Then hopefully we have time to go through some questions. Otherwise, I would have to spend more time on doing questions, but since you guys all have the stack, so most of the people just go through it. So, so peak to peak. and RMS. Voltage and the current and the power as well. Now, before we do that, you guys need to all familiar with the DC symbol for DC power supply and symbol for AC power supply. Because I checked yesterday and day before, not many people familiar with it. So symbol for AC power supply, like your sine graph there. Symbol for AC power supply, and just on the side, we know everyone knows symbol for DC power supply. DC supply is the battery for cells. Okay, now just draw AC, just the voltage, put it as a time scale time. That's your EMF. That's in volts. Now, before we do that, do we need to know the symbol for alternating DC? Oh, what do you mean by alternate DC power supply? There is no alternate DC. I mean, what do you mean by alternate DC supply, Nicholas? It's like something changing, varying? No, not necessarily, no. What we need is these two. Okay, AC power supply, DC power supply. Can the DC, yep. Okay, now I'll just ask a simple question. We know our domestic power supply is AC, right? Domestic power supply is AC. If I draw that, can you guys help me to label this value? The peak value, what's the peak value? Now, most likely you guys gone through at school this stuff. What's the peak value of the voltage that you receive in your household? It's not 120. Praveen, Kishan, Akshat, tell me, what's the peak value? Yep, Kishan, that's your right. Akshat, Asta, no, it's not 240. It's not 240, the peak value. The peak, the 240 volts is the what we call is the average or RMS value. 339, yes, Sujit. That's right. So that's about 339, close to 340. So that's what we call the peak value. We peak, or sometimes we can simply write OVP. That's the peak value. And double that, so the V peak to peak. Or sometimes we simply write VPP is equal to twice the peak value. Simple as that. That's from top to bottom, here to here. That's negative 339. Negative doesn't mean that you get negative power. The direction of the current flow is opposite, because your zero become more positive compared to that. The current flow going to be other way around. Now, so the common question is, what is the average voltage? If you look at that graph, if anyone asks you from year 8, 7, 8 kid, 9 kid, if we ask you what's the average voltage, simple answer is 0. Average voltage is 0. Because you got negative values and positive values. But we know that average voltage, yeah, it is, had to be 240. Yeah, it is 240. Then the question is, how do you calculate that? Now that's where RMS comes from. The current follow the same shape, guys. Current, the shape of the current variation is pretty much follow, not the magnitude, not the amplitude, but the shape will exactly like that voltage. RMS voltage, RMS stand for so root mean square value. It's a mathematical operation how to get the average for the varying function like this. Yes, varying function like this. Root mean square. This is the average or what's the other term? How do you explain this RMS value? This is the average or say for an example, your RMS voltage is 240. Let's say your household equipment can operate in DC power. Let's say your household equipment can operate in DC power. Then if you want to buy a big battery, you have to replace your AC power with 240 volts DC battery. So we saying that this is the average voltage or the DC equivalent voltage. It's called DC equivalent voltage. RMS value is the DC, yeah. It's your DC, yeah, DC equivalent voltage. That's correct, actually, yes. DC equivalent voltage. Okay, so let's see how we calculate the RMS value. So the VRMS is given by the peak value divided by root 2. How do we get this? Now, when we were people trying to get that RMS value, so we're looking at this voltage at any given point as a function of time can be written as the peak value, some sine function. So the voltage at any given time, the peak value, and it's changing that peak value as a sine function. So when they doing the mathematical simplification, so they do the square first. Square. They square the function. Why you squaring? To get rid of that negative part. You square the function so that they do that operation first. When you square it, everything will be positive. So when you calculate the errors, guys, that's what they do as well. Because if you have negative errors and positive errors, if you're trying to get the average, estimating average error, if you simply add all the errors, you get error 0. To get around that problem, what they do, they just square all the errors. Then all the negatives and positive become positive. So this is the same thing. Okay, so square it. Squared xt. Now we know that maximum value we can get for a sine function is going to be 1. What's the maximum you can get for a sine squared? So we do square, we go backward and take the mean average. What's the maximum value you can get for a sine squared function, sine squared value? Jaden, what's the maximum you can get for sine squared? For sine, you can get, yes, still 1. Still 1. So to get the mean value, you get the maximum and divide by 2. So to indicate it's a mean, we put a hat. Just to indicate that's the mean. So we peak, you get the maximum value. You divide by 2. And then finally you get the root, square root. That's what we call this RMS value. We peak, divide by root 2. So simply your RMS value given by we peak over root 2. Also we can write VRMS. So V peak is root 2 times VRMS. As a rule, remember I'm saying that not for, like it's like, see, you guys feel like how dumb I'm saying these things because I've seen these problems. At least remember, guys, the peak value should be bigger than RMS. You said, oh yeah, that should be obvious, but not obvious to everyone. But some people are making lots of mistakes, have no idea what's the relative size of the values RMS and peak. At least remember, peak value should be bigger than RMS. The peak has to be bigger than RMS. Okay, and then if you want to get the peak to peak, it's 2 root 2 times VRMS. The current is the same, IRMS, I peak over root 2. Peak to peak, I don't need to write. To the power RMS, so the IRMS, PRMS. So that's going to be I peak over root 2. B peak over root 2. So when you simplify that, I don't know, you guys can see that far. Oh yeah, can still see. So PRMS, power RMS, you can see it's a peak power divided by 2. We're not using that relationship that much. Okay. Now, in a question, if they say there is a power generator producing 1000 volts EMF, they're not mentioning anything, they're simply saying it's 1000 volts EMF. Power is 2.5 kilowatts. They haven't mentioned it's a peak. They haven't mentioned it's a peak to peak, but they haven't mentioned it's RMS. What are these values? A generator generating or producing, say what's the value, whatever the value I said before, maybe 5, yeah. The RMS values, absolutely. If they haven't mentioned anything about whether it's RMS or peak, we always treating them as RMS. If they have a peak value, they will mention it. They will state it. Otherwise, we treating them as RMS. I'll make up a simple, very simple question. Example. Maybe I'll give you this one is RMS here to be clear. Find the I peak flowing through the circuit. Just asking peak current going through the circuit. Now you guys need your equations back. R total. This is a simple series circuit. And V equals IR, Ohm's law. Don't need much, you need like basics of it. So there's a 200 ohm resistor and the light globe that has a resistance, just treat like there's a 50 ohm. Okay, so the RMS, is that a peak current? 0.07, Justin? Yep, I think you're right. Yep, that's good. Yes, 0.67. That's good. So what do? You calculate your RMS value. I suggest, like, recommend kids do everything in RMS and then finally convert it just to make it reduce the confusion. But you convert it to peak and you can work through it. But my advice is deal with RMS, find the RMS value, then finally at the end, very end, convert it. This is just to reduce the confusion. So our total here, 250 plus, yeah, so 250. And then you get your RMS. Well, divided by 250. I think that was 0.04 something. Therefore, I peak. I know it's a very simple area, but people are having trouble. I don't know why. People are not very comfortable with this RMS peak stuff. 6, 8. Okay. Let's refresh. So our generator. Producing, say, 50 kV kilovolts at just say 500 volts. That's okay. 50 kilowatts at 500 volts. Producing. So that's the generator. There's a bit of resistance in the transmission line, say 2 ohms. This is 200 ohms. What is the peak voltage received by the 200 ohm resistor? Maybe make it 20. 20 ohms. So I want to go buy an appliance and I'm looking for it. What it value is it? It is the RMS, yes. is the RMS value. And also generally, if you're going like Europe and you're buying appliances, just check the frequency as well, because sometimes the frequency have a bit of a variation, and also the obviously voltage. Now these days, most of the appliances can change automatically the voltage. Previously, you have had a switch because your US is using 110 or 120, and you come here 240. You had to have a switch to turn back to 240. Now these days it's pretty good, like it's just automatically changing back to 240. Okay, you guys see the numbers there, yeah? 50 kilowatts, 500 volts. There's a bit of a bright spot coming there. Find the peak voltage received by 200 ohm resistor. How much current going through the wires? I should have asked that as well. Maybe just first one, maybe find the ammeter reading. Can I make another number one there? Find the ammeter reading. That's the time. Yeah, need to be quick. Okay, so when what you will see on the ammeter? Okay, 2.2 amps. Okay, that's the RMS. Has to be RMS because all these values are RMS. Although I haven't mentioned anything, they are RMS values. So to find the current through the transmission line, you can use P equals VI. Okay, that's the current through the transmission line. Then that's 50 kilowatts. That's 50 times 10 to the power 3. Voltage is 500. The current, this is the RMS current going through the transmission line. So that's going to be 100, does it? Feel like 100. 50,000 divided by, so 50 to 500, yeah. Okay, got 500. Okay. 100. So the 100 amps going through it. What's the peak voltage received by 200 ohm resistor? Just find the RMS across 200 ohm resistor. I times R. So 100 times 200. 2,000, 20,000. So 220 kilowatts, kilovolts. Oh, that's not right. My numbers are crazy. Yeah, my numbers are not good. So VRMS is going to be 100 times 200. That's going to be that massive. Yeah. Forget about my numbers, guys. It's not going anywhere. At least find that. Maybe just say that's the unknown resistor. Let's say unknown resistor. Maybe find the peak voltage received by 20 ohm. That's not going to work. Anyway, forget about that question. My numbers not going anywhere. Okay. Okay, Nate, just a simple question. So you have the voltage RMS peak value of 500 volts coming through. Set of globes here. So resistor. Put another resistor there. Right, so just put that, say 50 ohms. These are 100 ohms. Okay, so find the current through. Find the peak current through each ammeter. Each ammeter. Find the peak current through each ammeter. Find the power. Make it 200. Find the power dissipated across 200 ohm resistor. Okay, now if you guys remember in parallel circuits, our total given by 1 on R1, 1 on R2, 1 on R3, you had to invert that. Just a quick recap of your simple electricity. Okay. Yeah, so is that what you get? 4,545. Oh, you get 100 amps. Yeah, for the 20 ohms, maybe correct. That's I squared R times 20. No, I don't think you get the right answer because when you get 100 as a current there, so 50,000 divided by 500. With 100. If you say unknown resistor, that would be better than 20. You get 2,000 ohm. No, I think my question was garbage. Okay, just go back to here. So, yeah, I think that numbers are not right. My numbers are not playing that well. Okay, so just work through. Find the resistance of these three first. Now, if you guys remember from last year, if you have two identical resistors, yeah, combined resistance become half. It's become 50. 1 on 100 plus 1 on 100. If you invert that, it's become 50. And 50 and another 50, it's become 25. 25, and then you add to 200. Maybe if you want to recap that bit. If you don't remember that, just use the normal standard way. Our total, this part, 1 on 50, 1 on 100, 1 on 100. That's become 25 ohms. Because I'm just using 100, 100, that's become 50. 50 and 50, that should be become 25. And then this is the total in this section. So the sum of our values. That's 200 plus 25. 225 ohms. That's the total resistance in the transmission line. Everything, your circuit. You can find the RMS value. Maybe deal with RMS everything rather than peak and at the end. That's always the safest way to do it. You can do it in peak value. Then you get the peak value here and the peak value. But I'm just So 353.55. If you use the peak value, of course, you get the peak values there. But I just trying to emphasize as a practice, deal with everything with RMS, and at the end, you can convert back to peak value, just reduce that confusion. And then I through the 200 ohm resistor, that will see the total current. Your total current depends on, these are all RMS values. R total, so V total divided by R total. So I total, what you measure is 353.55 divided by, what's the total I said? 225. That's your total current. 353.55. Anyone's comfortable doing with the peak, that's fine as well. 1.57. That's amps. So that's your A4 reading. That's RMS. And look at how much voltage you're dropping there. 200 ohm resistor. Voltage drop across 200 ohm resistor will be I times R. I'm just using everything RMS, no confusion here. 200. So I'm going to drop 31427 volts here. So not much left then. This makes sense because this whole thing is 200, this whole thing is 25. So the voltage drop across the remaining three devices, they're going to be parallel, they're going to share it. It will be 353, take away that. The voltage drop across the parallel part. I'm just giving this is the worst case, like you don't get match parallel series, like you get a simple series ones, maybe maximum you get one globe in parallel. So just to safe side, just to revise your electricity a little bit. 353.55. You get 39.3 volts. These are all RMS values. I did not take any peak values yet. This is 39.3. So everything clear as crystal because we haven't mixed up any peak values. They're all RMS. Now I can easily find my IRMS through each resistor. Then at the end, when I'm relaxing, I just convert everything back to peak. Yeah, when you're trying to find the power dissipated across, you can just do that question now if you want. I squared R or V squared on R. So the current was, what did I say? Maybe I didn't work it out. What was I told? Yeah, I did 1.5171 squared times 200. Just how much power you dissipated. Squared times 200. That's simply RMS power, 494 watts I'm dissipating across that. Now I'm going to find the current through each device. A1, the voltage is 39.3, the resistance is 50. 39.3 divided by 50. I get 0.786 amps. Now keep in mind, if you can remember Kirchhoff's current law, the current through each branch should add up to the total current flowing here. IA2 obviously should be half that because it's 100 ohms, but you can work through and divide by 100. You get half that. And then IA3, don't need to work it out again because it's the same resistor, 393. These are all RMS values. And also we know IA4 was 1.571. Now you get all your values. Now start working through and calculating the peak value. IA1 peak is √2 times that number. IA2 and IA3 peak value. These are all peak values. √2 times 0.393 and IA4 peak value. .571. Yeah, so you get the answer. That's what I said. When you do deal with everything in, okay, yeah. So you need to consider that parallel nature. So when you simplify that first and then add to that 200. Okay, when you do everything in RMS, you don't feel that tension. Okay, I just mixed up or peak value with RMS. So you dealt with everything with RMS, everything RMS. You know that you haven't mixed up anything. At the end, you can convert back to peak value. That's the cleanest way to do it. Okay. So the power dissipation, that those are RMS values. All right, so we have to move on to transformers. Any confusion, guys? Anything to clarify in here? You don't need much about series and parallel, but just have a bit of a brush up. That's all. Little bit. Mostly we're dealing with kind of series. Yeah. Because part of the electromagnetism, because we going through power transmission, yes. Under power transmission, you're getting like a simple parallel series circuit. They're not complex or little ones, but you need to have a reasonable handle on to deal with simple circuits. It's way simpler than what you dealt with the 11, but still, because most problem is you forgetting things. Okay, we'll move on to the transformers. Can I wipe it, guys? Yeah. Okay. I know some schools that they're going through circuits again for year 12, but you don't need much on circuit, but you need some knowledge. Okay, transformers. Now, the basic principle, operating principle of transformers. The basic operating principle is electromagnetic induction. which is Faraday's law and Lenz's law. Now, what's the purpose? Purpose of a transformer? Is either to increase the voltage without changing the power, we call a step up, or decrease the voltage, or step down. Step up or step down. Okay, so the transformers are using quite widely everywhere in your household, in big power transmission lines, in your laptop, because your laptop is using DC power, but that's a different story, but using low voltage. So when you connect into your main power, your battery charge, your phone charger. So when you connect into 240 volts, so the laptop I'm using here, it's using, I think about 20 volts or something, 20 or 40. I can't remember, my eyesight is not that great. Yeah, so you can see the transformer is incorporated. I think you guys can't see that one. Transformer is incorporated in your brick, in your laptop. You can see it's heating up. Some power is losing there. But we saying that transformer is ideal in our year 12 classes. So you can increase the voltage or decrease the voltage. Okay, step up or step down. So basic skeleton of a transformer is pretty much similar to what Faraday's first experiment. Now transformer has a core made out of soft iron. This is a soft iron core. And then I'm just still drawing the core. The core is not a solid block. The idea of the soft iron core is to link the magnetic flux change in the primary coil. That's what we call the primary. So you have, this is very important device here. This is AC power. AC power supply is utmost important thing, important device here. AC power supply. Without the AC power supply, you can't have change in magnetic flux here. You need to have change in magnetic flux. So this device is replaced with the DC power, your transformer will not work. Your transformer will not work. You need to have the AC power supply. So this side is what we call the primary coil. The right-hand side is where we supplying that our output. This is what we call the secondary coil. This is the load where you're supplying your power. It could be a calculator. It could be a laptop. Some other device is a secondary. I might have asked your question. How do you recognize the primary side of the coil against the secondary side? When you look at the transformer, how do you say, oh, that's my primary side, this should be secondary side? Praveen, tell me. How do you identify? Yeah, it's easier something, yeah. I get primary connected to the primary side connected to the power. Yes, that's immediate answer. The primary coil has to be connected to the power supply. The primary coil has to be connected to the power supply. The secondary coil is connected to the external circuit. Primary coil is connected to the power supply. If you look at the actual construction, what will happen when you're turning on? So there is a current going through it. As a result, if you use the right-hand slap rule, there's a magnetic flux. That magnetic flux will nicely link into the secondary, like that. That's the purpose of the core, to link the flux variation in the primary to the secondary coil. So the magnetic flux variation soft iron core it links the magnetic flux, the change in magnetic flux in the primary coil to the secondary. It is necessary to have this AC power supply. To produce that change in flux. Change in flux. Okay. All right. If you look at the actual construction of the core is not one solid block, as I said. Why? Because whenever there is a change in flux, we know that change in flux happening in the body of the core as well. The body of the core as well. When that happens, when there's a change in flux happening in the body, what will happen? There will be induced current in the body of the core. If there is induced current, what will happen? Because it has a resistance. The core has a resistance. Then it will start to heat up. When that heat up, some power will be losing as heat. So they want to minimize that. What they're trying to do is they're trying to, like a laminated structure, they break these one core into like a biscuit parts, layers. Each layer can take the magnetic flux and supply to the secondary, but there is no current building up between the plates because there is an insulating glue between these plates. It's called laminated structure. Laminated structure to reduce the we call the eddy current, the current that forming on the surface. If you guys, I don't know whether you guys can see it. Can you see that lamination? That's the core. That's the core, but you can't, I don't know, it's not that great. You can see that plates, put them together. I see number of plates, put them together. So it's not a one solid structure. So laminated structures, that they're not going to ask you a question about this eddy current, how to reduce the eddy current, but just for your understanding, to laminated structure in the core to reduce the heat losses. Laminated plates in the core will minimize induced current in the core. So heat losses will be less. To minimize the induced current, these are called eddy currents. The induced current, the term they're using is the eddy current. All right, that's that. So we need to come up with the equation now. Now, I'll say this is the primary side, that's the secondary side. Now we assume that the transform is ideal. That is assuming there is no heat loss. It's not 100% true though, but we are assuming transform is ideal. So that means the power input in the primary coil is same as coil is equal to power out in the secondary. Very coil. Okay, power input is equal to power output in the primary. Okay, now we go back and write the values. So this is my primary side. That's my secondary side. So the power in the primary, this is PP, is same as power in the secondary. And VP, or sometimes use V1, that's the voltage in the primary. Input in primary. That's the VS, the voltage in the secondary. IP, the current in the primary. IS, current in the secondary. Number of turns, NP, number of turns in the primary, number of turns in the secondary. These are the information in the primary coil and the secondary coil. Okay. Now, since P is PS, now keep in mind, guys, sometimes we using the terms, I don't know, should I write here? Instead of writing P same as V1, IP sometimes replace with I1, NP replace with N1. So you can see that those terms coming up. VS with V2, IS with I2, NS with N2. So sometimes we see these terms as well. Okay. So in terms of the function, you guys need to know when the flux suddenly changing, the induced current producing a magnetic flux to oppose that. So then there will be AC. Produced EMF will be AC here. So get rid of this. I need some space. So power in the primary, power in secondary. Therefore, I can say P equals VI. You guys remember this equation, yes? I can write V primary, I primary, VS, IS. Therefore, I can write an equation VP on VS. Remember, it's IP, IS on IP. It's flipped the other way around. And also, we know that induced EMF is proportional to the number of turns or number of wires, coils. So therefore, I can write VP proportional to NP. VS is proportional to NS. And based on that, you can write another equation. If I remove that proportionality sign, introduce a constant, the constant will cancel. They're following the same direction, NP on NS. So at the end, I can write this equation. Is the final equation, NP over NS, VP over VS, IS on IP. Okay, you can flip the whole thing other way around because it's a simple ratio. Or N1 on N2, V1 on V2, I2 on I1. So that's the type of equation you can use. Stick with the one that what school is using. So anything is fine. And then you can flip it the whole thing, the ratio. Okay, maybe I'll give you a simple question. I can get rid of this, I guess, yeah. Now, the symbol for a transformer, guys. Hey guys, now power transmission question. N for number of turns. N is the number of coils. Number of turns here. N is the number of turns. Okay. This is number of turns, coils. Bigger the number of coils, the greater the induced EMF. Okay. Symbol for transformer. Now, what I was trying to say was last year's power transmission question. was, I don't know, was one of the hardest question for kids. One part of the question, I don't think more than 3% people got the full marks. There's a simple question asking what modification you suggesting to reduce the power loss or something, without changing your plans, without changing any equipment. But I think not many people answer that well. Simple for a transformer, so they can use either like a two people are handshaking or something. This is the virus edge, just keeping close. There's the AC symbol and just the external part. So this is the part generally using for transform. The symbol, this is like indicate the core, or you can use simply that. So I tend to use that. Okay, step-up transformer has more coil in the secondary. In the secondary than the primary. Step down is opposite. So in a step up transformer, your NS is bigger than NP. I'll stick with my little n. I should have kept capital, that doesn't matter. NP. Switching between capital and simple. Let me just do that. Yeah, I'll stick with capital. That's fine. It doesn't make any difference. Okay, so step up transform, more coils in the secondary. Remember, since in a step up, using a step up transformer, guys, you keep the power. Oh, it's gonna be P equals VI. Your power stays constant. Your power stays constant, your voltage is increasing. When you're writing your answers, use of the step-up transformer, you have to mention keeping the power constant. Or either you had to use the word for same power. Okay, listen everyone, you have to use the word for same power or constant power. Increasing voltage will reduce the current. That's the advantage of a step-up transform. The power stays constant. You have to write that. Otherwise, you don't get the full marks there. For constant power. Right there. The power stays constant because it's ideal. But you increase the voltage. Hence, the current will decrease. Because simply P equals VI equation. For same power, increasing voltage will reduce the current. Some words to give the idea, the power stays constant, but you are increasing voltage, therefore it reduces the current. There are specific words Vika is using, Vika is expecting in your answers. Remember, one of the question was the circular shape of an electron going through the magnetic field. They expect you to say constant force. And that force is perpendicular to the magnetic field or perpendicular to the direction of the motion. If you don't use the word constant force, you lose a mark. Okay, if you don't use the same power, you lose a mark. Okay. All right. I'll give you a simple question. Example. We have a transformer. This is the ideal transformer. All the transformers are we treating as ideal. If they ask you to draw a step-up transformer, guys, at least show more coils. More coils there. Say they say N1 is say 100. N2 is say 600. Look at the simple turn ratio. The power is say 600 watts or something, and then the voltage here is say 60 volts. Find the V secondary. Find Vs. Give me a quick answer. The equation is Vp on Vs, S on Ip, and P on Ns. Give me a very quick answer. 360, 1 to 6. Okay. 360 Akshat. Okay. You guys all wrong. Okay. Yep, Jaden's correct. Okay. Anyone else? Yep, Akshat, that's better. Yes. Yep. Anyone else? Elu hit that. Did you pick up the problem? The answer should be 0. I just want to highlight again, if we connect the DC power supply to the primary, there will be no induced EMF in the secondary. Okay. So that's why you guys generally go blind when you see the transformer question, not paying much attention. So what will happen, you just calculate and get the number, but you get 0 marks. So just keep an eye. This is commonly they're putting in, it's very common. You suddenly put a DC power supply here. You get a tiny bit of current, but there won't be any steady current there. The answer is 0. So maybe just change that to AC now. In that case, if you use the AC, N1 on N2, V1 on V2, it will be 360. So that's 100, 600, 60 to Vs. 360 volts. Okay, now find part B. Find the peak current in the secondary coil. Find the peak current in the secondary coil. 2.3. Okay, let's see. Maybe correct. 600 divided by 360 times by. Yep, 2 point. Yeah, that's correct, Lohit. Akshat, yeah, all good, all correct. Yes. Okay, so find the RMS current, IRMS. The power is the same. Power in the secondary, same as, so that we know that I is secondary, V secondary. That's same, 600. We're looking for the current. These are RMS values. And it was 360. And then 600 divided by 360. That's RMS, and then convert back to peak. .66. 67 amps. That's the RMS. And the peak current going to be 2.36. Okay, that's fine. Now, rather than I'm making up these wrong questions, if you guys have this worksheet with you, how long we have? We have half an hour. Yeah, 2:31. Okay, we have half an hour. That's fine. Can you get this transform worksheet? There are scribbled answers on the side, but that's fine. Get that transform worksheet with you. I just emailed that this morning. We do a couple of questions and then I'll go through power transmission. Once you start getting hang of it, like how to apply the questions. Okay. Can I drag it to 145? Anyone want to run it quickly? No? Yeah? Okay. So that's a transformer. So there are number of turns in the primary, 1000. I'm mixing up NP, NS, N1, N2, just to get used to the symbols. And then N2 is 100,000. And then you have a primary voltage. The transformer is connected to 120 volts, means that's the primary. 120 volts. They simply asking for the V2. Look at the ratio. So 1000 to 100,000. This is like 10 to the power 3 increase. So this voltage has to be 10 to the power 3 increase. If you feel like it's annoying, like changing symbols, like you stick with one, whatever convenient for you. Ten to the power 3, 10 to the power 5, so 120. 1.2 times 10 to the power 4. Look at the simple ratio. Get used to that, looking at the simple ratio. The voltage will be increased by the same ratio. The current will be decreased by the same ratio. The power stays constant. The voltage will be increased by the same ratio, and the current will decrease by the same ratio, and the power stays constant. Question 2. Transformer made out of 200 turns. primary winding, that's N1 or NP is 200. 50 winding is in the secondary. Is it a step up or step down transformer, guys? 250. So immediately you need to recognize that's a step down transformer. Okay, step down. I get answers, so much of answers coming up. Who's answering? Is it Akshat? Okay. Good, he's giving answers. He's in a poll. Okay. What's Thastisara saying? Did I miss something? Okay. You guys are answering the which question is that? Maybe the previous one, I'm not sure. You're answering a different question or the previous question? Akshat, which one you answering? I'm not sure. It looks like I missed something.
All good.
Ah, you send it down to Stitcher. Okay.
Yeah.
Yeah. Yep. Okay, that's good. That's good. Okay. 250. So the question is, the primary voltage was 120. So the N primary is 120. Secondary current was 0.12 amps. What's the primary voltage in the second? What is the primary current? They're asking for IP and secondary voltage VS. So you look at the ratio. That's 4 to 1 ratio. The voltage will be dropped by a factor of 4. So if you 130 divided by 4, that's going to be 30. But we'll do it properly. So NP on NS, PP on VS. That's 200 to 50. PP 120 for VS. $30. And then asking for the current as well. So NP on NS, IS on IP. Whenever you step down, the current will go up by a factor of 4. That's the factor of 4 current. So that means you need to divide by 4 to find the current, which is divided by 4.03. So the NP is 200, 450. IS is 0.12, IP 0.03 amps. Okay, question number 3. An ideal 2.25 transformer changes 120 to 4.5. That's a step down. If they ask you to draw a step down, you need to show less coil, less turns in the secondary. The power is the same on either side. So the voltage is changing from 120 to 4.5. You can look at the ratio. What is the current in the secondary coil? You can just P, you only go for P equals VI here. Like 0.5 or something. 0.5 amps. Part B, they ask you to find the turn ratio. You can use that turn ratio. They're asking for NP on NS. $120 over 4.5. Close to 27 according to this. Yeah, 26.67, just round it up to 27. 27 to 1. Number of turns come here. Round number. We close to this whole number. Okay, question number 4. Now, this is a multi-choice question. Ask you to figure out which one is correct. It's a step-down transformer. Now, the step-down transformer is required to operate a halogen lamp. So that means that's your load here. The lamp is there. That means 25 watts. And the voltage is in the secondary is 12. And you can quickly work it out what the secondary current is. 25 divided by 12. Something like 2 point something. 25 divided by 12. So 2.08, the secondary current. Now the primary current has to be smaller because you're stepping down. When you step down, the voltage becomes lower, current becomes bigger. So the current here should be smaller than 2.08. Okay, they're saying which are the following conditions could apply for this transformer. The first one, it's a multi-choice. They're asking which one is correct. NP, they're saying 20. NS is 200. That's a step up. This is a step up. That can't be right. You're looking for step down transform. That answer is wrong. So VP is 120. IS they're saying is 0.21. We worked it out. IS was 2.08. So that can't be right either. Because we know that IS is that. .08. That can't be right. Answer 3. IP and IS is same. That's never be possible. Not possible. What's the purpose of using a transformer otherwise? Answer 4. VP is 120. VS is 0.21. Oh, that's the units are wrong. There should be amps. IP. Yeah, VP is 120. That's quite possible. If that is 120, the ratio is 10 to 1. The current should be 10 times smaller. If you divide by 10, that's going to be 0.21. That seems right. So that answer is right. So the answer should be D. Question 4 answer should be D. Maybe I'll move on, quickly go through power. Power transmission lines, okay? Power transmission lines. Okay, I'll expect you guys to finish, but quickly go through power transmission lines. Now, the power transmission question, guys, at the section that we are learning in year 12, main focus is to understand how do you minimize the power losses. Because when you're transmitting power from a generator to hundreds of kilometers away from the region, suburbs, towns, some power losses happening. Okay. Power transmission. So we generated the power. We dealt with what's this AC, RMS, all these values. Now we talked about how to use the transformers. Now we're talking about how we transmitting this generated power to far distances. So main focus is how to minimize the power loss. Okay. Let's consider a generator. Okay, that's a generator. Maybe producing 5 megawatts of power at say 5,000 volts. That's the frequency of the generator producing 5,000. That's fine. And then you try to transmit that power to some suburbs and towns somewhere, very far distances. These are the regions that you're trying to send that power, transmit that power. So you install some power transmission lines and install a step down transformer. These guys using 250 volts. I'm just getting a round number, make it easier. Step down transformer. So the stepping down from 5,000, that's the purpose, to 250. That's the turn ratio. And then you connect your power lines and transmitting through. And then supplying to these homes. So that's your transmission line. So again, the problem is there is some resistance in the transmission line. Not much. So each line has a 1 ohm resistor. Each line. Now, when you're dealing with this question, guys, please consider this as simple series circuit. It's like essentially that's your generator. And this is your transmission resistance in the transmission line, 1 ohm each. And that's the load. That's where you're trying to find the supply, the power. These are the houses, the town. That's simple as that. That's your circuit. Until your, maybe just until your transform. Okay. Until your transformer arm is here. And then your suburb houses. That's your step down transformer. That's how what your circuit is. Now, again, the question is going back. We'll break this question into several parts. Find the current through the transmission line. Transmission line. Hopefully my numbers should be match up. I'll quickly double check, but you guys can work it out while I'm making sure my numbers okay. Yeah, I think that's not too bad. Yeah, I think that's fine. This question is okay. Find the current through the transmission line. Okay, now what equation you guys can use? What equation you guys can use? I'll give you a bunch of equations. You have P equals VI, V equals IR, P equals I squared R. Now these are the equations that you guys need, apart from that simple parallel and circuit, series circuit. What that bright patch, I can't get out of that. P equals VR. Those are the equations. Which equation that you're going to use? Can you use V equals IR? Can you use P equals VI? Now people are having SAC, you need to answer this week. Why? Praveen, tell me. You can turn on your speaker and talk.
Because the two in the middle are for power loss,
Okay.
and the first one, we don't know the current. Oh no, wait, but we do have the.
We're trying to find the current, yes. You're right. You have to use P equals VI. Why can't I use V equals IR? Because I'm trying to address a common problem I see throughout the years. Now, some kids using V equals IR, they're using resistance to be 2 ohms. What's the problem? What is the problem? If I use V equals IR, if I use the resistance as 2 ohms, what I'm saying is all my 5,000 volts, I'm going to drop across this 2 ohm resistor. My total resistance is, R total is 2 ohms. I'm dropping that all 5,000 here, the transformer will get nothing. Therefore, people here will be in dark. They don't get the power. Do you understand what I'm saying? That's why you can't. If you know the voltage drop originally across that resistor, then you can use V equals IR. If you knew, as Praveen said, if you knew the power loss beforehand, then you can use I squared R. Otherwise, the safest equation is, well, I don't know, can't say safest, recommended equation, okay? I'm not saying you can't use it, you need more information. Equation is P equals VI. Okay, that means you supply 5,000, you supply, that's my power, you find the current through the transformer. The current will not change, but the voltage will be changing based on the drop at different locations. The current will not change. So if I use P equals VI, the power will be 5,000. Not 5,000. 5 times 10 to the power 6. That's 5,000 times I. Next question. Find the power loss across the resistance. Now, why is the power loss? There are 2 reasons. One main reason, because of the resistance in the transmission line. Why there is a power loss? In the transmission line. Because there is a resistance. Because there is resistance. The resistance, if you guys can remember, proportional to a quantity called resistivity. It's a material property. So if I use aluminum cables, maybe copper has less resistivity. The gold is better. So are you recommending to replace all the transmission line with gold? Would be good. The people are rich in that area too soon. So that's not going to work. Or you can use thick wires. Thick wires has less resistance. The resistance, if you have a greater resistivity, greater resistance. But resistance is inversely proportional to the cross-sectional area. Is a cross-sectional area. If I take a wire, that's a cross-sectional area. Bigger the cross-section, that means thicker the wire, lesser the resistance. It's very expensive. If you recommend to replace all the cables with thick wires to overcome this power loss issue, it's going to be a massive cost. What's another problem? Thicker the wire is heavier. Then the wire is going to sag. You need to apply tension once in a while, go and tighten these wires. And then sometimes the dry time, because remember that the bushfire, one of the reasons for the bushfire was the poorly maintained power lines, because the trees and the plants in those times, when they comes in contact with these power lines, because they're sagging, so you can catch a fire. So especially during the dry time, it can convert into a big bushfire. So this changing the wires you can recommend, but not very practical. The length of the wire again contribute to the resistance. Longer the wire, that's the length. We can't say that bring the suburb close to the power station. That's not practical either. You can't shorten the wires, yeah. You can't say, can you bring the constructor? Someone said that, one of the year 12 kids, not this year, a couple of years ago, just build all the houses around the generator. That's not going to work here. Yeah, lots of pollution. This is there. You see the carbon, the coal. Okay, that's not the biggest actually culprit. The biggest culprit is the current, high current. There's a resistance. However, the main reason for power loss is the larger current. In the power line. Guys, you have to get used to this graph. They're testing power loss. Because power loss is given by I squared R. It's linearly changing with the resistance power loss, but it's almost quadratic. It's quadratic because it's I squared with the current. You need to get used to this graph. It's going square relationship. Okay, square relationship. Okay. Important for your SACs, yeah. So how do you minimize the current? That's the question. Okay, how do you minimize? That's where step-up transformer comes in. So if I go back and find the power losses, we use the P equals I squared R. The current was 1000. The resistance is 2. You simply add them together. If people having SAC this week, sometimes they can give the resistance per kilometer. resistance can be given per kilometer. In that case, you need to times by the length. And then if they say 4 kilometer distance, then you have to get 8 kilometers back and forth. Okay, 8 kilometers back and forth. Okay, I squared R, that's 10 to the power 6. That's about 10 megawatts, 2 megawatts. 10 to the power 6. I think Mount Trail, you guys having SAC this week at the same time as well, yeah? Lohit and Lojit, yeah? Is that electric power SAC this week? Yes, yeah. So question is how to minimize the power loss. That's where you install a step-up transformer. Loss. You can say reduce the resistance. Not that practical, but it's true answer. But reduce the current in the transmission line. I wouldn't mind people who having SAC this week, have a look last year's week exam question. They're simply asking what changes you could make, very simple change, but it's a good thinking question. Reduce the current in the transmission line by installing a step-up transformer near the generator. Accordingly, you have to change the step-down transformer as well. Because if you keep the same step-down transformer, it's not going to work. You have to replace the step-down transformer to obtain the voltage at the to safe operable level. Okay, operable level. So, do you have time to? Can I quickly install a step-up transformer here? So that increase the turn ratio to 1 to 1000. Now, we might not have the time. At least keep in mind, if we increase the turn ratio by a factor of 1000, your voltage will increase by a factor of 1000. That means 10 to the power 3. The current will reduce by a factor of 1000. 10 to the power 3. Your power loss will be reduced by how much? Factor of 10 to the power 3 squared. Your power loss will reduce by 1,000,000. 10 to the power 6. Because the I squared. If you have, I don't know, 3 megawatts was losing before. It just 10 to the power 6 will be now. We will reduce by 10 to the power 6. If you have time, shall we quickly work through? What's the initial power loss? I think we worked out 2 megawatts. Now find the new current through the transmission line. So you're feeding 5,000 volts, and then find the secondary voltage. The VS at the step-up transformer. Now the turn ratio become 5 times 10 to the power 6 to 250. So your VP over VS, NP or NS, your VP will be 5,000. I'm trying to find VS. NP is 1 to 1,000. That's the turn ratio. Did I make a mistake? Yes, VP over VS. No, that's correct. So VS is going to be 5 times 10 to the power 6. That's your VS going to be 5 megavolts now. Find the new current through the transmission line. In the line. Again, go back to P equals V. Yeah, your power hasn't changed. For same power, the power hasn't changed. 10 to the power 6. Voltage was now 10 to the power 6. The current become 1 amp. Previously 1,000 become reduced by a factor of 1,000. How much the power loss now? Question 3. New power loss. Well, let's go with I squared R. If they ask you to find the voltage drop, you can. If you know the current, you know the resistance, that's V drop. Previously, you had 2 megawatts, 2 times 10 to the power 6. Now, what are you getting now? Now 2 watts. You can see 1 millionth less. 10 to the power 6 less. Yeah. Okay. All right, maybe I'll stop there. People are leaving, want to leave. There are questions I attach, power transmission questions in the worksheets, in the email. And also the generator, that's a good one. Some of the questions were coming from different states, New South Wales, Queensland, Victoria. Some of the questions that came in recent other school sacks. So, and the questions are pretty good. I would at least spend about an hour and a half, go through that, some of the questions. Some of the questions are multiple choice, but good questions. Very good questions. Power transmission questions are good. Power generation questions are good. Some people got that booklet. I don't know how many people got that big booklet I intend to supply. Some people may not. This booklet, some people might have got it, some people not. I can email parts of it if you haven't received it. But if you have enough material to practice, go for it. If you start face-to-face classes, maybe I can supply, but that's going to be too late for some people. At least you can use it for your exam revision. Okay, maybe I'll stop there. Good luck for people having SAC this week. Mount Waverley, Melbourne High. I don't know other schools. I know that Mount Box Hill, you guys just finished your SAC here. Okay, I'll let you guys go. If you have any question, you can text me or email me. Hassle me, that's fine. When you when you find the power loss, the value is RMS. Yes, RMS. We always deal with RMS unless they ask you something peak. Always RMS. That's what I said. Do not confuse. Deal everything with RMS. If they peak, they will ask you. They will tell you to find. Okay, that you do at the end. When you're leisure, have a coffee, then do it. Okay, don't rush to put the peak values and then mixing up them. That's my recommendation. Deal everything with the RMS value. At the end, if they ask the peak, then convert it. Okay. All right, I'll let you guys go.
Thanks, sir.
Bye, bye, guys. Yeah.
Thank you.
So,
Yeah. Kishan, you got a question now?